So now we're going to discuss how to compare all the different modulation formats and their performance that we've seen so far. How can we come up with a good metric that says how one may be better than the other? And to do that, we need sort of a gold standard, something we can compare it to, and we'll see that QPSK will be our gold standard for the probability of error. So QPSK is a reference. This is because QPSK is, first of all, very popular. It has some very good characteristics, and it's often used in systems. But most of all, we just need a benchmark, and it's a good benchmark. And it allows us to quantify performance vis-a-vis something that's well known. So if everybody knows QPSK, everybody has a good feeling for how good it is, what kind of signal-to-noise ratio it takes to achieve a certain quality of transmission. Well, then if I say this is 3 dB worse, 4 dB worse, it's an easy way to get an intuition for the next modulation format, which may be less common, less well known. So let's look at the union bound and what it tells us about QPSK. Here's the general expression for the union bound, and here it is when we plug in the values for dmin and k for QPSK. So QPSK is basically the Q function of the square root of 2 EB over N0. And the multiplicative number in front is really not very important because this Q function has an exponential decay, which is much more important than the multiplicative factor in front. So just to recall that the dmin was 2 to the square root of EB, and when we normalize it to the lowercase dmin, that comes out to the square root of 2. So square root of 2 is this normalized distance for QPSK. So if I were to write the equation, the Q function now with the dmin inside of it, recall that this comes right from the a union bound. It's not just for QPSK, but here it is for QPSK in particular. We can put this dmin on the inside of the square root. So here's the 2, and that's directly related to the dmin lowercase squared. So this is our reference point, our basis of comparison for other modulation formats. So let's first take a look at M-QAM, in particular rectangular or square QAM. So we know the form of the receiver. For QAM, it uses IQ in phase and quadrature branches on the receiver. So a cosine multiplication and a sine multiplication, 2 branches, because it has a signal space of dimension 2. And the performance we found for an arbitrary sized square QAM constellation was given by this expression. Again, a multiplicative factor out front, and then the Q with the square root of 3 log 2m divided by m minus 1, which is, remember, what multiplies EB over N0. So if I wanted to look at what is it that multiplies EB over N0, that is by definition what we call this dmin lowercase squared. And for this, here I have it written in L. Remember, L squared equal M, so either expression works. So let's start comparing 2 specific modulation formats. Let's take QPSK, and one of the first square modulations we looked at was 16 QAM. So I would like to see what the little dmin, the normalized dmin, is for these 2 modulation formats. And QPSK is essentially a QAM, a square QAM modulation. It's just 4 points. So we could use the same general equation. We could plug in m equal 4 or m equals 16, and we would get an expression for the dmin. And of course, we've already done this for QPSK. We get the square root of 2. And what I'm going to do with the dmin for 16 QAM is to make it something times the square root of 2. So it's the square root of 4 over 5. But the square root of 4 over 5 I'm going to write as the square root of 2 times the square root of 2 over 5. So whenever I get a dmin, what I'm going to do is I'm going to take it and I'm going to put some factor times the square root of 2. Because this is the difference compared to QPSK. So this is the QPSK value. And how different is it from QPSK? Well, that's what I'm trying to identify. That's why I'm writing it in this particular format. Now, if I want to take that difference and I want to put it in units which are convenient, what I'm going to do is I'm going to write it in terms of dB. Because remember that the EB over N0 is a measure of signal to noise ratio. And we typically write that in terms in decibels. And now this multiplicative factor can tell us about almost like a loss in EB over N0 because vis-a-vis QPSK. So in particular, we'll take minus 10 log 10 of whatever's under the square root. And in this case, it's 2/5. And that gives us, 2/5 of course is less than 1, which is going to give us a negative logarithm. And so that's why the negative sign is out front. And I call it 4 dB, and I call that loss. Of course, if I called it gain, then I wouldn't have that minus sign getting rid of it, and it would be minus 4 dB. But we like to define it as a positive quantity, which is the loss. Of course, there may be possible that the loss is as defined negative, which means it's really a gain. So don't be confused by the minus sign. It's just a convention how we talk about these factors. So in particular, QPSK versus 16 QAM, I can say that if I have a certain performance level at QPSK, if I switch to 16 QAM, it will take 4 dB more EB over N0 to get the exact same performance as QPSK. So that means that QPSK is much more efficient in terms of bit error rate than 16 QAM. And we can quantify how much more efficient based on this loss factor. And again, it comes from this expression. So it's great to be able to quantify the difference between one modulation format and another, but it's another thing to even look at it graphically, which is even more helpful. So remember, here is the QPSK waterfall curve. You can see the yellow one is QPSK. And I plot next to that this purple or pink curve, which is the bit error rate versus EB over N0 for 16 QAM. And if I look, asymptotically, let's say that I'm getting down to fairly low BERs, and I look at how much is one curve displaced vis-a-vis the other one, well, that is this loss that we're talking about. So here we can see graphically, this was produced using BERT tools in Matlab. We can see here the 4 dB penalty in the probability of error that we found theoretically previously. So here I'm plotting the whole Q function. And I know approximations, the Q function as defined is the integral of the Gaussian density. And of course, if I'm up here at fairly terrible performance, 10% errors or something like that, the difference between them, is not going to be this level that I've calculated. In fact, this value that we came out here is the asymptotic loss of 16 QAM versus QPSK. So it's really meant to be looking at here. But you can see that when we get to values which are of interest in communications, probability of error of 10 to the minus 4, minus 5, minus 6, that's where we're already in this regime where this loss vis-a-vis QPSK, this expression for the lowercase d min, is giving us. So it's telling us how far apart these curves are. So I really, if I have the QPSK curve, I really could get a pretty good approximation of it just by moving it over by 4 dB. Yeah, so if I moved it, looks pretty much the same. Might be off a little bit up here, but still it gives us a good approximation. So that means that intuitively, if we know what it takes in our system to get into this region for QPSK, we know it'll just take 4 dB more to get the same performance from 16 QAM. So I looked at 16 QAM, but we can make the exact same calculations for any of these squares, because square QAM constellations, because I have an expression for it. It's very, very easy. I have a day min closed form solution for M QAM. And so I just plug it in now for L equal 8 or M equals 64. And I get 18, the square root of 18 over 63. And again, I separate it into two factors, one of the factors being the square root of 2. And the other, I look at what's under the square root. That's 9/63. I plug it into my calculation for loss, and now I see I'm up to 8.4 dB loss. So going from 16 QAM to 64 QAM, I'm getting a much bigger loss in this case, which I can visualize again graphically if I prefer. And this is the difference between these two curves. And now asymptotically we can see for 64 QAM it's moved way over. There's 8 dB of loss compared to QPSK. Keeping on going, I could go up to 256 QAM. And in this case, I do the math and I come up with 13 dB of loss for 256 QAM. So you can see that as we're making a larger and larger constellation with square QAM, the penalties are going up very quickly in dB. And so here with 256 QAM, it's 13 dB of penalty. Very, very widespread. So now suppose I ask a question another way. Suppose I tell you that QPSK needs 9.9 dB of EB over N0 in order to reach probability error of 10 to the minus 5. You know, I know QPSK, I know how it performs, and I have in my head, oh yeah, if I want to get down to 10 to the minus 5, I've got to have like 10 dB of EB over N0. That's pretty noisy channel, but that's okay. QPSK is very robust. That's one of the reasons I said it's so popular, and it'll get me down to 10 to the minus 5. And now I say, well, what will it take for 256 QAM to get down to 10 to the minus 5? Well, I know that it has a loss of 13.3 dB. Okay, it's 23.1 dB, a fairly strong channel in order to get the same performance when I go up to 256 QAM. So, you know, I put it that way, and now I see how useful this comparison is, this figure of merit being the loss compared to QPSK. You know, now we have great tools in Matlab, and I can go to Matlab, use Bertool, and say, plot for me the curve for QPSK, plot for me the curve for 256 QAM. It's not that difficult, but in, you know, I also know it theoretically, which is why this other way of approaching it can be very helpful to develop intuition. So in this case, if I looked at 10 to the minus 5, and in Matlab I generated the two curves, then I can look for 10 to the minus 5 and say, oh yeah, if I want to get 10 to the minus 5, the curve with QPSK, I only need 9.9 dB. But if I were going to use 256K, of course, I'd need 23.1 dB. So I could use Matlab and I could read those two different numbers directly. But if I have the opposite, I don't have Matlab, but instead I only have the QPSK curve. In that case, I can sort of answer the question even if I don't have access to a complete solver. I can just say the difference between them I know is 13.3 dB, and so I can figure out that to go from 9.9, as I did just now, I just add 13.3. In this example, which comes from one of the previous exams, I give you a QAM constellation, which is not one of the QAM constellations that we've seen before. So in this case, you would have to, one of the questions is to find the minimal distance for this constellation. And in fact, once you find the regular d-min, I also ask you to normalize it and to tell me what the small d-min is. And then finally, assuming that we have EB over N0 equal to 13 dB, I ask you to find the probability of error for 3 constellations. There's another point, there's another part of this problem, but I just want to show you now that, you know, I showed you how to do the normalization for square QAM. So I showed you how to take these coordinates, which are IQ coordinates, and how to, first of all, if I look at just the geometry, I could ask myself, is this distance here shorter than the distance here? So which one of these is smaller? Because I'm looking for the minimal distance. And, you know, I'll let you do the math, but you can see where this simple coordinates of plus and minus 1 might help you to do the trigonometry to figure out, are these 2 points closer together or are these 2 points closer together? And I'll let you do that. And you'll pick which one is the d-min. So you'll know if it's this one or this one. Then, this is not the right normalization. This is IQ space, not signal space. So next step will be to do the normalization. And so you have a nice equation for that. You take the distance from the origin for all of these different points, and you find the normalization factor, and then you have a multiplicative factor that tells you what the how to go from IQ space to signal space. And then you would take whatever this d min is in these IQ coordinates, and you would convert them into that d min in the signal space. And in the signal space, it'll be a function of ES, or you could write as a function of EB. Okay, so that's the first part of the question. Find the capital D min, which will be a function of ES. Second part of the question is the small d min. And the small d min is all about normalizing it to get rid of the EB over N0 and be left with a dimensionless quantity. And then the last part, the B part, is to compare it, to find the probability of error. I don't say here directly to compare it to QPSK. However, you do have, when you take the exam, a curve for QPSK. And so you can look up, if you don't remember that what the 13 dB and EB over N0 for QPSK gives you, you look it up on this curve, and then you know what performance you can achieve, and it'll tell you what the performance is here, because you can always calculate the loss compared to this. So again, this gives you the ability to take QPSK as a reference and use it to quantitatively compare with other constellations. I will tell you the answer to this problem ends up being this expression for d min. So d min, if you go through and do the math here, do the normalization, convert, you will get that it is the square root of 1.27, which is the minimal distance. So with the minimal distance, you can calculate the loss of this constellation compared to QPSK. So I take the square root of 1.27, I separate out this factor of 2, so it's the square root of 0.635 times the square root of 2. So I know that the loss is minus 10 log 10 of this factor, 0.635. Remember, it's the factor under the square root, and that comes out to close to 2 dB. So I know that if I compare this constellation with this constellation requires 2 dB more EB over N0 to get the exact same performance. So I could, as I mentioned, go to Matlab and get the plot for QPSK, and I could use the day min, put it into the Q function, and ask, and use Matlab to plot the bit error rate for this other modulation format. And I could look at the particular performance at the EB over N0 equal to 13. So that's what was asked for in the question. If I have this 8 QAM, and I look at, I want to know what is the performance at EB equal to 13. Well, I know they're 2 dB apart, so that I know that that would be where QPSK had 11 dB. And so now, I don't have this purple one maybe in my exam, for instance, but I do have this orange one, which is provided, or which I know because I'm familiar with QPSK. And I know that if I had 11 dB EB over N0, then that means that I would get something like 10 to the minus 7 bit error rate. So if I've gone through the process of finding the minimal distance, I essentially know what I need in order to get the performance of this sort of different looking QAM. So I have the big d min, and I normalize it to get the little d min. From the little d min, I calculate the loss, and I see it's 2 dB. So I take this orange curve, and I know that the pink curve, if I were able to plot it in Matlab or some other routine, that it would just be 2 dB to the side. So you'll recall that I showed you with the union bound this expression for the probability of error square QAM, and I mentioned that in ProACUS we could find an expression for the exact probability of error, and it was in fact the same. So in this case, the bound gave an excellent, was actually equal to the real value. Now, if you look in Sklar, you'll see on chapter 9 and these pages, he gives a probability of error which looks slightly different. And I just want to be careful because Here it's the probability of error per symbol. This is symbol error. This also is symbol error. And this is bit error, assuming that we're using a proper mapping from bits to symbol. So it is the same expression, and I just want to make sure that coming from different sources that you can appreciate that they are in fact equal. Okay, so now let's summarize some of the information that we've gathered about bit error rate for different modulation formats. And in particular, I just generated this curve using the BER tools command in Matlab. So BER tools has a nice routine where you just tell it which modulation format and it'll plot it for you, and you can compare them all. And so here we go from BPSK and QPSK, which are superimposed here. This 8 PSK is the purple one here, 16 QAM is the red one, and then we have 16 PSK and finally 64 QAM. So when we put them all together now, we can, with this plot, sort of see what we're trying to learn about this loss compared to QPSK, because I can see graphically what that means. So here's QPSK. I can see how much I have to move over, how much the loss is for 8 PSK, and I notice that for 16 QAM, it's just a little bit more. So I can look at this, I can see this from the plot. And my point is that this loss compared to QPSK is a little bit like looking at these plots and saying how much worse, how much farther over are these plots. So if I have them with me, if I can easily plot them, I'll look at it this way. But the quantification of the loss compared to QPSK is another way of presenting the same information.